Today's session of Global Noncommutative Geometry Seminar, and our speaker is Adam Skalski from Mathematical Institute of Polish Academy of Sciences. And the title you can see, Translation Invariant Noncommutative Dirichlet Forms. Please. Adam.
Thank you very much, Richard. Thank you very much for the invitation. It's a great honor for me to speak at this seminar. So I decided I will talk about the joint work with Ami Wisselter from the University of Haifa in Israel. That's something we've been working on with Ami for a few years now. And the general idea is I will try to describe a certain class of quantum probabilistic evolutions, by which I will mean here Markov semigroups on von Neumann algebras. Again, I will give a formal definition in a second. They act on von Neumann algebras. They also act on associated LP spaces. And in particular, we will focus on examples coming from locally compact quantum groups inspired by classical Levy processes and classical convolution semigroups of measures. And what I want to talk to you about today is various ways in which you can describe generators of such objects, of such Markov semigroups. Again, in particular, focusing on so-called quantum Dirichlet forms, which will be translation invariant. So let us start by talking a little bit about classical Markov semigroups and Dirichlet forms. So suppose that we have a measure space. The measure mu can be a probabilistic measure, but in some examples we'll have in mind, that can also be an infinite measure. So just think about, say, the Lebesgue measure on the real line. And by a Markov semigroup, for the purposes of this talk on X mu, I will understand the family of operators which act on L infinity. So that's an algebra of essentially bounded functions on X mu, and which satisfies the following conditions. Well, first of all, this forms a semigroup in the usual sense. We always assume that our evolution starts from identity. So P0 is identity, and PT plus S is PT composed with PS. The second property is natural continuity at 0. And this natural continuity here for us, because we are in a von Neumann algebra, is a weak star continuity. So for a pointwise weak star continuity, so for every function f, the limit of PT of f on weak star topology is f again. And the last assumption is that this is a semigroup of contractions. So each PT is a contractive operator. We also assume that each PT is a positive operator. Right? So it maps positive functions or non-negative functions into non-negative functions. And finally, PT also interacts nicely with the measure we have. So if you compose mu with PT, you get another probability, another non-negative measure. This non-negative measure is dominated by mu. So whenever you have a Markov semigroup in this sense, so I defined it on L infinity, but the point is that it also acts on all LP spaces where P is between 1 and infinity. And we shall call the semigroup symmetric if on the easiest LP space, namely on L2, this will consist of self-adjoint operators. Okay. So as we know from the study of operator semigroups, if you're interested in studying such semigroups, you can study them via their generators. In particular, I said that they act on all LP spaces, so you can essentially choose on which LP space you want to look at these generators. And naturally, the easiest case is that of the Hilbert space. So assume for the moment that PT, well, this will be the assumption for most of this talk, that PT is a symmetric Markov semigroup. So remember, that means that each PT as an operator on L2 is self-adjoint. And consider the following expression. So what I do, I essentially take a scalar product of F with F minus PTF. And I take a limit of this expression when I divide it by T and let T go to 0. So this need not exist for all F, but under the assumptions we had, we can show that this limit will exist for a dense subspace of L2 space. Now, moreover, this expression, and I also note that for every F, if this limit exists, I mean, this limit is just a number. So essentially, we found a way in which, for at least for nice functions, to every function, we can associate a number. This association has some nice properties. Namely, Q is what's called a Dirichlet form. This is a densely defined quadratic form, which is closed. That's a kind of natural condition for which we know again from the theory of generators of C0 semigroups. It's real, by which I mean that if you start from a real function f, then Q of f will be a real number. And moreover, it has this property which essentially reflects the Markov property or the positivity property of the original PT. Namely, if you consider a projection from L2, from say the real valued L2 functions, onto those functions which lie between 0 and 1. So this is really going to be, this can be easily described geometrically. You really take a function, and when it's below 0, then you put 0. When it's above 1, you put 1. So this is a nice convex, closed convex set in a Hilbert space. So definitely there is a projection onto it. And our form satisfies this property, that when you apply this projection to any function f, which is in the domain of Q, then you get some number which is smaller. Denis, almost, well, 70 years ago, showed that there is a one-to-one correspondence between symmetric Markov semigroups on L infinity and Dirichlet forms on L2. Now, what is the advantage of studying Dirichlet forms? Well, in general, it's easier to work with quadratic forms than to work with unbounded generators. It's easier to perturb them, to manipulate them. So this theory classically has been developing and is still developing today. So what about the example? I want to talk about particular examples which are related to groups. So suppose that we have a locally compact group G. I want to also think about G as a probability space. So I need a measure on G, and it will be always a Haar measure. You have a certain choice, but I will most of the time assume, well, actually all of the time assume that we are working with the right invariant measure on G. So I have a locally compact group, which I can think about as a measurable space as well. And when you have a family of probability measures on G, you call it the convolution semigroup if it satisfies the following conditions. So again, the first condition is just the semigroup property. So when you want to look at the measure which corresponds to T plus S, this is just given by convolving measure mu T with the measure mu S. And it satisfies natural continuity at 0. So the measure at 0 is supposed to be just a Dirac measure at the neutral element. And you have pointwise convergence on all functions vanishing of infinity, so all on C0 functions. So this is what we mean by convolution semigroups of measures on G. Now, again, these are very natural objects to study, namely because they are precisely distributions of Levy processes. So stochastic processes with independent, identically distributed increments. Now, given such a convolution semigroup of measures, you can associate to it a Markov semigroup in the sense I described before, and that's a Markov semigroup of the corresponding Levy process. So how do you do it? Well, essentially PT is nothing but the operation of convolving with the measure mu T. So remember that mu T is supposed to be a probability measure for us here. So all these PTs will be in particular unital maps, and the convolution property of measures translates into the semigroup property of these PTs. So by Berling-Denis, we know that to each such, to each Markov semigroup of this type, so to each convolution semigroup of measures, we can associate a Dirichlet form. And it's a natural question, which Dirichlet forms are those which appear in this way. And these are precisely those which are characterized by certain translation invariants. All classical for the moment. The next thing I want to say is that, well, if you're working with the convolution semigroups, you can not only look at Dirichlet forms as their generators, but you can also do something much simpler. Namely, so once again, let G be a locally compact group. Suppose that we have a convolution semigroup of measures. The next theorem, which here was first proved for the real line by Levy and Khinchin, and then generalized to arbitrary Lie groups by Hunt, and then to arbitrary locally compact groups by Heyer, is the following. So if I have such a convolution semigroup of measures, I know that this limit, mu T of f minus f of e, this limit of just this expression in the nominator is always 0 for every function f, which is continuous and vanishes at infinity. But it turns out that if I try to differentiate this expression at 0, so if I divide by t and try to check what happens, then still this limit exists for all sufficiently nice functions. So this exists for all f in a certain domain. And what I want to stress here is that this domain always contains all compactly supported twice differentiable functions. Now, you might wonder, I mean, what does it mean twice differentiable? If I talk about locally compact groups, I mean, it turns out this is essentially the work of Heyer. There is a natural notion. You can essentially realize any locally compact group as a limit of Lie groups in a suitable sense. And you can define abstractly the algebra which plays the role of, say, twice differentiable functions on any locally compact group. And then it turns out that whatever convolution semigroup you choose, then this limit will always exist for every function which is twice differentiable. Now, this functional gamma, when I know it on the whole domain, or in fact, even if I know what it does to these functions here, this determines uniquely our convolution semigroup of measures. Now, if G happens to be compact, we can replace this algebra of twice differentiable functions by a smaller algebra, which is very nice, namely by what I call Pol G, and you can think about it as coefficients of trigonometric polynomials on G. Formally, I mean coefficients of finite dimensional representations of G. Now, in particular, there's one thing that I want to stress because it will be important for us at the very end of the talk, namely that the domain of gamma of this functional, again, note that gamma takes a function f and just produces a number, right? Not another function, just a number. And the domain of gamma always contains a nice dense subalgebra of C0 of G. Right? So not only a dense subspace, that's something that we are familiar with from many aspects of study of unbounded operators. I mean, they should have dense domains, but here we also know that this domain contains a subalgebra. Okay, so now let us go quantum. So throughout the talk, M will denote a von Neumann algebra, and we will most of the time assume that it has a fixed normal semi-finite faithful weight phi. If you don't know what weights are, these are non-commutative counterparts of infinite measures. You can also think about the situation when this weight is simply a state, namely a bounded positive normalized functional. But again, because we are interested in the locally compact world, it's also natural to allow the possibility of working with weights. And I will say that an operator T from M to M is Markov if it's a positive contraction. So again, it has norm smaller than 1, and it maps non-negative elements of M to non-negative elements of M. And I also assume that it interacts nicely with this reference weight. And here's the formula. Because T is positive, I mean, there are no problems with interpreting this formula. You can think that phi, you can compute the value of phi on any positive element. Well, it may just be infinity on some of them. And again, more or less for technical reasons, or because the quantum world looks as it does, it's also important to have the assumption of, often it's important to have the assumption of complete Markovianity, or of complete anything essentially, namely to assume that not only this T behaves well, but this nice behavior of T persists after you lift it to matrix algebras. So in particular, here it means that, well, instead of considering just M, I tensor M with a finite dimensional matrix algebra. So I just consider essentially n by n matrices over M. I have to equip it with a reference state or weight. And what I do, I take my original phi on M, and I take just a normalized trace on Mn, if you wish. And you want the same properties as above also to hold for these liftings. So this is what we will mean by, this is precisely what we will mean by complete Markov. Okay. So what do we do next? I want to spend just a little bit of time on discussing LP spaces. My talk will not really contain much information about LP spaces beyond L infinity, L2, and L1. But maybe because these objects we consider, they do live on all LP spaces, it's worth to spend 3 minutes on talking what one should mean by that in the non-commutative context. So suppose first that we are in the easiest situation, easiest non-commutative situation, namely that our weight, our reference weight, is in fact a trace. So it's a functional, potentially unbounded, but it has this property that for nice A and B, tau on AB is the same as tau of BA. This is the tracial property. Then it turns out that you can define LP spaces simply as certain completions of M. M is L infinity. And let's assume for the moment that the trace is also bounded. Then this expression really makes sense for every element X in M. This gives you a certain number for each X. You can check, it's non-trivial, but also not very difficult, that this is indeed a norm. And you can define LP space to be the completion of M with respect to this norm. Now, in the non-tracial state case, the situation is somewhat more complicated. Namely, the formula, if you write the formula just this way, you can try to do it, but it will fail to be a norm in general. So you can define LP spaces in various ways. One possibility is you can just say, well, I know what L1 should be. L1 should be the predual of L infinity. So let's say that L1 of M is the predual of M. And let's define LP spaces as interpolations between L1 and L infinity. By L infinity, I will always understand M itself. Of course, this requires some way of embedding of L1 of M into M, or just realizing them on inside some space. And that's the approach that was taken by Araki, Kosaki, and also Izumi. You can also try, it's kind of conceptually very nice to realize these LP spaces as some concrete spaces of operators. And that's something that was done by Kohn and Hilsum in the 1980s and also by Hogerup. If we are in the non-tracial weight case, again, the approaches above still, you can make them work. For us, I mean, we will focus on the Hagerup LP spaces. So for me, this LP of M5 will always denote the Hagerup LP space. Again, I will not give a formal definition of what these are. These are certain concrete spaces of operators on a certain new Hilbert space, not the original one on which M was represented. What's important is that there is a way of embedding M into LP of M. Well, strictly speaking, we are not embedding all of M. We are embedding only so-called P-integrable elements. And what we will work with today is mainly so-called KMS embeddings, namely the embeddings which are in a certain natural way symmetric. So you have a certain kind of magical operator D here. This D can be thought of as the density matrix of the reference weight. So for example, if your von Neumann algebra M is B of H, then you know that any state on B of H is given by a trace, canonical trace on B of H, together with a density matrix. And that's kind of, well, very vaguely speaking, this D you see here is the density matrix of our weight. Formally, it's the generator of the unitary group, which is related to the modular automorphism group of phi. Essentially, again, all that I want you to remember from this slide is that, well, there is a construction of LP spaces, and there are certain embeddings. One can have a choice of which embeddings to consider, and we will consider this particular one, the symmetric embeddings of M or good parts of M into the relevant LP space. I should have said it earlier, please feel free to interrupt at any point. I do not see the chat questions, so if there are any, then just please say them loud. So we saw before that for the Markov maps, then classically, the nicest ones to work with are those which act in a particularly kind way on the associated L2 space. So the same happens here. So given a map from M to M, I will say it's KMS symmetric if its KMS incarnation, which is given formally by the formula here. I will explain to you in a second what it really means. Gives you a self-adjoint operator on L2 space. So essentially, it's just that you have an operator on M. I will say it's KMS symmetric if once you put M in this KMS way into L2 of M, you obtain a bounded self-adjoint operator. So in particular, for the formula above to make sense, you want this T2 that I define here is kind of behaving really nicely with respect to these embeddings. And now a quantum KMS symmetric Markov semigroup will be a pointwise weak star continuous semigroup of normal Markov maps on M, such that each of these maps, each of these individual maps is KMS symmetric. Now, what is the advantage of working with these? Well, first of all, on a Hilbert space, we get a genuine semigroup of self-adjoint operators. And moreover, KMS symmetry gives you some automatic realization of certain conditions we considered. So for KMS symmetric, and if you're a positive contraction, then automatically you respect your reference weight. Now that this property of KMS symmetry involves the weight. The weight is somehow hidden. You may say that the L2 space of M phi, well, you can think of this as some realization of a standard form of M. But the way you embed M into this space definitely does depend on the choice of the weight. Now, when you have such Markov KMS symmetric semigroups, to be precise, when you have completely Markov KMS symmetric semigroups, so again, everything works equally nicely after you tensor with matrices, these act on all LP spaces. Right? So again, we have the situation that we formally start with something that happens on M or on L infinity, but you get things on all LP spaces. Okay. So the next thing we want to say is Dirichlet form. So what I want to say now is the following. So I said a second ago that when you have such a KMS symmetric Markov semigroup, then it acts on all LP spaces. In particular, it acts on L2. It acts on L2, so hence you can associate to it a certain densely defined closed quadratic form. Now, the next aim is we want to understand what makes this quadratic form a Dirichlet form. And this definition came, again, more than 20 years ago, was introduced more or less independently, although in a slightly different context, which I will explain in a second, by Fabio Cipriani and Staszek Goldstein and Martin Lindsay, who said that, well, a quantum Dirichlet form for such a pair M phi should be a densely defined closed quadratic form on L2 M phi, which is real in a certain suitable sense. You have to, on this space, you have a natural way of identifying what are the real or self-adjoint elements. And moreover, it satisfies this condition. So that's again the condition we might remember from the classical Dirichlet theory. Now, this P wedge is again the orthogonal projection from L2 of M, from the real part of L2 of M, onto, before we had something like 0, 1, now we really think about the interval between 0 and the square root of D. This plays the role of 1 in our L2 space. So that's a definition. I said that they work in slightly different contexts because Goldstein and Lindsay worked specifically with the Hagerup spaces from the beginning, whereas Cipriani considered standard forms. And here's a theorem. So that was proved by Cipriani, Goldstein, and Lindsay in the state case. Then it was extended by Goldstein and Lindsay to the weight case, and also with Ami a tiny bit in the end. So that's now fully general for whenever you have a von Neumann algebra M and you fix a faithful normal semi-finite weight, there is a one-to-one correspondence between completely Markov KMS symmetric semigroups and quantum completely Dirichlet forms as defined here. So I didn't say what's a completely Dirichlet form, but again, I guess, I hope you can guess. So once again, it means that, well, you tensor with matrices, you put here the trace. There's a natural way of extending Q to this new L2 space, and you assume that the Dirichlet condition is still satisfied. So the fact you are densely defined and closed and real, that will be automatic for this lifted form. But we also do assume that this Dirichlet condition, the most important one, is also satisfied for these matrix liftings. Okay. So for the moment, that's you may say, well, that's potentially a useful way of describing generators of such completely Markov KMS symmetric semigroups, but can they be useful? And the answer is yes. So I just want to give you one example. There are actually several examples of applications of quantum Dirichlet forms, mostly in the tracial context. So in the study of von Neumann algebras, it's often important to consider certain evolutions which come from semigroups. And in the tracial context, that has been well known for, again, probably at least 20 years, that these can be used to study properties of von Neumann algebras. But you can also do things for general, not necessarily tracial von Neumann algebras. So here's an example, a result we proved a few years ago with Marta and Kaspers, that which says that if M is a von Neumann algebra, the Hager property, which I'm not going to define here, because that's just to show you an example of how these things appear. The Hager property is a certain approximation property of a von Neumann algebra. And the second equivalent condition is that whenever you choose a faithful normal state, then this pair M phi admits a quantum Dirichlet form of a particular type. So below is a formal definition, but again, you do not really need to read anything beyond these 2 points. The point is that properties of von Neumann algebras, even those which at first glance have nothing to do with any semigroups and evolutions, can be sometimes described using the language of quantum Dirichlet forms. And here's an example of a result of this type. So now we will be moving to the translation invariant situation. So the setup is as follows. From now on, G will denote a locally compact quantum group in the sense of Johann Kustermans and Stefan Vaas. I will not be giving a formal definition once again. I just want you to know that these are certain objects which are studied in terms of operator algebras. The key object, and in fact the one which appears in the Kustermans-Vaas definition, is a von Neumann algebra I will denote by L infinity of G, which is equipped with the coproduct or co-multiplication, namely a certain unital normal star homomorphism from L infinity of G into the tensor product of L infinity of G with itself, which is co-associative. And in fact, L infinity of G together with delta, that already carries all the information about G. We also assume that this pair admits what's called the right-Haar weight. So it's a certain weight on our von Neumann algebra, which satisfies natural invariance conditions with respect to our coproduct. To a locally compact quantum group, it turns out one can also associate in a canonical way other operator algebras. So in particular, we have a corresponding C-star algebra, which we denote C0 of G. I'm not explaining the motivation behind these notations. I mean, I think you can guess, you can all guess, why do we choose these symbols and not the other? So we have something that should play the role of continuous functions vanishing at infinity. This is a C-star algebra, in general not unital, which is densely contained in L infinity of G. The quantum fact of life is that sometimes you also need to consider the universal version of C0 of G. So you can have two versions of continuous functions. Now, one thing which will be important for us in a second is in particular that this is this universal one which admits a particular character called the co-unit, which classically corresponds to evaluating the function at a neutral element. So these guys sometimes coincide, sometimes don't. Have a surjective map from this one onto that one, but in particular, this guy need not admit this, the co-unit. Okay, two more notations. So to G, we can associate also natural Hilbert space. If you wish, this can be defined, for example, as the GNS Hilbert space of the right invariant Harweight. I will also write L1 of G for the predual of an infinity of G. What's also important is that this L1 of G admits a natural Banach algebra structure, which classically corresponds to convolving functions and is determined by our map delta, which acts on an infinity level. This is really just the convolution product is a predual, if you wish, of multiplication. So here is just these things that I said, that C0 of G is always contained in an infinity of G, and L2 of G, this is in the language that I was using on previous slides. This is the L2 space associated to L infinity of G together with this fixed right invariant Harweight. Okay. Two more general definitions. So it turns out that the theory of Kustermans and Vaz admits a perfect duality. Namely, to each such locally compact quantum group G, you can associate the dual locally compact quantum group G hat. Now, what is important, what will be important for us is that both these algebras, which describe G hat, they can be viewed as subalgebras. They can be viewed as acting on L2 of G. This is the same Hilbert space. Another way of saying this is that we have a canonical isomorphism between L2 of G and L2 of G hat. And that's a quantum version of the Plancherel theorem. The Fourier transform gives us really the canonical isomorphism between L2 of G and L2 of G hat. So what are these things for classical locally compact group? Of course, every locally compact group is also a locally compact quantum group. So here, L infinity of G hat turns out to be the von Neumann algebra of G. C0 of G hat is the reduced sister algebra of G, and C0 universal of G hat is the full group sister algebra of G. So this example in particular shows you that in general, we do have to distinguish between this reduced and universal object. If G were abelian, then sister reduced is isomorphic to the universal sister algebra of G. In general, this is not the case. Okay. So now, let us mention what happens in the compact case. That's a case that I guess more of you will be familiar with. Namely, we say that G is compact if C0 of G is unital. So I will always just write it just as C of G. I mean, the functions vanish at infinity, but okay, there's no infinity. Equivalently, this reference weight, the Harweight, is a state. So this is an innocently looking additional assumption, but in fact, it simplifies the theory a lot. And the theory of compact quantum groups, due to Voronovich, actually predates the theory of Kustermans and Vaz by more than 10 years. And one of the big advantages of the compact theory is that this can be, these objects can be described in purely algebraic terms. So they can be described via Hofstar algebra, canonical Hofstar algebra, which sits in C of G. It always admits the co-unit. And you have, when you restrict our co-multiplication to Pol G, it takes values into the algebraic tensor product of Pol G with itself. And as I said, we do have the co-unit always. And the importance of this we will see in a few seconds. Okay, so this is the compact situation. So once again, I mean, the message for us is that when we study locally compact quantum groups, we do have to work with operator algebras, whereas in the compact case, a lot of the theory can be described on a purely algebraic level. Okay, so let us talk about convolution semigroups of states on compact quantum groups. So what were classically convolution semigroups of measures? Well, first of all, they consisted of probability measures. So we know that in the quantum world, the role of probability measures is played by states. So here we'll talk about convolution semigroups of states. Namely, this will be a collections of states on Pol G. That's what I want to say in the beginning. I could equivalently here write the universal version of C of G. So I could write Cu of G here. There would be some, and we will see something like this in a second. But let's stick to this Hopf algebra for the moment. And again, we assume that mu t plus s is the convolution of mu t with mu s, and this convolution is defined in terms of the coproduct as follows. We assume natural continuity at 0, so that's just pointwise continuity. And we assume that at 0, we always take the counit. Remember before, I mean, at 0, we took the evaluation at a neutral element, and that's precisely what's going on here. Now, when you have such an object, when you have such a convolution semigroup of states, you can always associate to it a convolution semigroup of operators on pole G. So this is a formal definition, and that's easy to check that they do form a semigroup. Moreover, it turns out that all of them extend to operators on L infinity of G. So remember, pole of G is sitting inside C of G inside L infinity of G. So these guys map pole G into pole G, but in fact, they extend to operators on our von Neumann algebra. And these form a completely Markov semigroup. So, okay, we can take, if we wish, the theory of Cipriani, Goldstein, and Lindsay, consider the associated Dirichlet form. And again, that this Dirichlet form will contain in a natural way pole G in its domain, and it can be characterized and studied purely using the language of algebras. And that's something that was done was exploited to a certain extent a few years ago by Fabio Cipriani, Uwe Franz, and Anna. Okay. Now, what's also interesting is that these convolution semigroups of states, they admit generating functionals. And again, that's something we saw classically. Namely, you can try to differentiate this family mu t at 0. Now, the magic, or in other words, the fundamental theorem implies that this limit will actually exist for all A in our Hopf algebra, in our pole G. Moreover, this gamma, when you view it on pole G, this determines the semigroup uniquely. And there is a not too difficult way to characterize those functionals on pole G which arise in this way. So formally they're characterized as Hermitian normalized conditionally positive functionals. Again, I don't want to spend much time on explaining what these words mean. The point is that we do have a full and easily verifiable characterization, which allows us to say, well, which functionals on pole G generate convolution semigroups of states. Now, this allows us to define and study probabilistic properties or analogs of probabilistic properties of the associated semigroups. So, for example, such things as we can define what we mean in this quantum setting, compact quantum setting, that a given convolution semigroup of states is Gaussian. Now, this turns out to be very closely related to certain cohomological questions regarding this Hopf-star algebra. And somehow, if you want to look at these definitions, or if you want to study cohomology, it's actually very important that you can define this gamma. I mean, it has as a natural domain of definition an algebra. If we want to study cohomology, we better have an algebra to play with. Okay. So let us now go beyond the compact case. So we are revisiting definition of convolution semigroups of states. Now I no longer have my algebraic object. I no longer have my pole G. So I have to work with states on C0U of G. So this is the universal version. Now, the reason why I have to work with the universal version is that, well, this is a natural space on which quantum probability measures live. Some of them will be living on the reduced object, but not all. I mentioned before that we should think about the counit as a Dirac measure at the neutral element. And in general, it only does live on the universal object. It does not define a bounded functional on the reduced one. So, okay, so we work on C0U of G, and then we can just write the same formula as you saw before in the compact case. So mu t plus s is just given by convolving mu t with mu s. Mu 0 is just a neutral element, it's just the counit. And we have pointwise continuity at 0. Now it turns out that even in this locally compact setting, such convolution semigroups admit generating functionals. So you can always write this form. You can just ask where, you can just say, well, we define the generating functional, this formula whenever this limit exists, right? So for A in the domain is precisely the set of these A where this limit exists. Then it's not completely obvious that this limit will exist for a dense set of elements in C0 U of G. That's actually not too difficult. What is kind of even less obvious is that this, once you have it, then this will determine the semigroup uniquely. But that's something we proved with Martin Lindsay, again, maybe 15 years ago. So always in this situation, you can differentiate on a dense star subspace of C0 U of G. And once you differentiate, what you get will determine the semigroup uniquely. That doesn't mean that there is an easy way of reconstructing mu-t from gamma. It just means that abstractly, if you know that gamma, if you know that two gammas come from two semigroups, then they will be identical, even only if the semigroups are identical. Note that this theorem does not say anything about the characterization of those gammas which arise in this way. For the moment, we don't know, and in fact, we still don't know. I will say something in 10 minutes about the results that we have at the moment. Now, for G compact, we already saw before that this limit exists for all A in pole G. So, of course, pole G is contained in the domain of gamma, but usually this domain of gamma will be larger. So remember, even classically, we said that the domain of gamma contains all compactly supported twice differentiable functions. Elements of pole G are always smooth functions, right? So that's the domain of gamma will be bigger in practice. Okay. So now I want to say something. So for the moment, I talked about semigroups of measures or of states. Now I want to talk about convolution semigroups of operators. And here is what is known. And essentially, this next theorem is a consequence of results of other people, primarily Matt Dawes, Marius Junge, Matthias Neufang, and Zhongjin Yuan. So there is a one-to-one correspondence between convolution semigroups of states on C0 U of G. These were these objects I defined a second ago. Then nice translation invariant semigroups of completely positive maps of norm 1 on this universal guy, C0 U of G. Also, semigroups of normal unital completely positive maps on L infinity of G, which are again translation invariant. And here the translation invariance condition, this is what you see here. It's actually easy, very easy to write it on the von Neumann level. So in particular, these are what I called before completely Markov semigroups. And you can also view corresponding objects on the level of L1 of G. So we have this kind of very nice correspondence. You can think, I mean, these families of maps, I mean, they're so nice that they act on everything inside. So they act on, you can view them just as states, you can view them as convolution operators on C0, on L infinity, or certain, kind of, again, convolution type operators on L1. So this, sorry, so the translation invariance here is, this last part is hidden by this property of being a left module. Okay, now I wanted to say something about, we kind of want to say something about symmetric or KMS symmetric maps. Remember that in my theory, I said that quantum Dirichlet forms, I mean, they work nice for symmetric objects, or for KMS symmetric objects for me. So let us start by saying something more still quite general. So if I have a state on C0 U of G, I can always write this operator, P mu. So here I'm cheating a little bit because I want to view P mu as acting on a von Neumann algebra. If you think about, if you think for a second about what I wrote here, I mean, the syntax, I mean, that doesn't parse, but one can make sense of it, kind of informally. This is what's really going on. That's a convolution operator determined by mu. And that's always unital, completely positive, and phi preserving. Here is the next statement, which is already interesting, namely that without even assuming anything about mu, the KMS implementation of this operator is always bounded So what we did, we have an operator from L infinity of G to L infinity of G. Now I'm building its KMS implementation. So that's an operator acting on L2 of G. It turns out to be bounded. Moreover, it turns out to belong to the von Neumann algebra of the dual quantum group. So I said before that these guys act on the same Hilbert space. So this in principle is possible, and this indeed happens. So essentially, I mean, the way you can think about this is that this algebra, von Neumann algebra of the dual group, is really built of convolution operators with respect to measures on our original thing. Now, the last thing I want to say is that I said we'll be mostly interested in KMS symmetric situations. And it turns out that there is an easy characterization of when such P mu is KMS symmetric. Namely, this happens only if mu is invariant with respect to the so-called universal unitary antipode, which again, classically is something which plays the role of the inverse operation. And again, classically, all it means is that the convolution operator is symmetric on L2, even only if it comes from the symmetric measure which is invariant under the inverse operation. So now we are ready for the main result, which concerns Dirichlet forms. So suppose that G is a locally compact quantum group. Then there exists a one-to-one correspondence between the following objects. So the first class is the class of convolution semigroups of states. But now I assume that each of these states is invariant with respect to this unitary antipode. The second thing is the nice completely Markov KMS symmetric semigroups on L infinity of G, which are translation invariant. KMS symmetry is always with respect to this relevant Haar weight. And the last one is the class of completely Dirichlet forms, which are invariant under the unitaries in the commutant. It turns out that this is from the computation under the commutant of the von Neumann algebra of the dual group. So now we have a full characterization of Dirichlet forms in the quantum setting, which really come from convolution semigroups of measures. So perhaps I will now try to tell you quickly about certain examples we can study using this result, or actually what are the classes of objects it really describes, and then spend the last 5 minutes talking about the generating functionals once again. So what happens in the commutative case? What are the objects that we describe in the commutative case? Well, as I said before, convolution semigroups on L infinity of G, they really correspond to a particularly nice class of stochastic processes of G on G, so-called Levy processes. And all these convolution semigroups are described via the formula of Levy-Khinchin and its generalizations due to Hand. So here we can actually give a very, really a classification of all convolution semigroups. How do they look like? And give probabilistic interpretations to various elements of this class. Now, in the dual case, what happens in the dual case? So remember that in the dual case, what I mean by this is I take a classical group, but I look at its dual group, which is described by this formula. So essentially, I'm looking at convolution operators, quantum convolution operators on Vn of G. Now, that's another class of very well-known and deeply studied transformations, namely the so-called Hertz-Schur multipliers. So all these convolution semigroups are of the form written here. So lambda G, these are generating unitaries in Vn of G. So these are just translations indexed by elements of G. And our convolution semigroups are Hertz-Schur multipliers of the following type. And this psi, which appears here, is a so-called conditionally positive definite function. And again, these have abstract descriptions, and again, they have been studied a lot. Now, the corresponding Dirichlet form here is as expected. I mean, it's really given by this quite simple formula. So you just take the integral, weighted integral of the square of f with respect to our reference conditionally positive definite function. So what about some quantum examples? So I just want to describe one way of constructing examples, namely the one coming from cocycle twists. So this uses a beautiful result of Kenny DeComer from his PhD thesis. Namely, Kenny showed that when you have a locally compact quantum group and when you have a unitary 2 cocycle on G, which is an element of this von Neumann algebra, which is naturally invariant under the, or satisfies a cocycle relation with respect to the coproduct, then in fact, you can obtain a new locally compact quantum group in the following way. You keep the algebra structure as it was, and the only thing you do, you change the coalgebra, you change the coalgebraic structure. So you change the coproduct in the following way. So that might be dual to what I'm sure many of you are used to the situation where when we deform the product to construct an interesting non-commutative algebra. So here you might say we didn't change the algebra at all, but you see that's not, well, it's true on the von Neumann level, it's still the same algebra, but for example, the fact that we changed the co-multiplication means that the corresponding sister algebra, so C0 of G, will in general change. And here is the connection of this construction with what I discussed before. So if you start from a convolution semigroup of operators on an infinity of G, in the sense I described earlier, and if it satisfies the natural invariance property with respect to this deforming cocycle, then you obtain a nice, again, a convolution semigroup of operators on this deformed object. So once again, I mean, I haven't changed my family on the level of an infinity of G, but the fact it's a convolution semigroup with respect to the new coproduct, that's, I mean, here it's actually quite easy, but that's kind of the new ingredient. So in particular, it means that the corresponding semigroup on the level of C0 or the corresponding states, I mean, they really will genuinely change. So here's an example of an application. So if you start from a object, I mean, actually, if you start purely by a classical object, by a commutative algebra, then nothing interesting will happen because you see, I mean, this will just commute to here. I mean, omega is unitary, so nothing will happen. So let's start from a kind of classical but non-commutative object, by which I mean you start from a dual group to a classical one. And when you have such a locally compact group G, which contains an abelian subgroup with a non-trivial 2 cocycle, then using some further ingredients, some nice positive definite functions on G, you can build interesting convolution semigroups on quantized Heisenberg groups or on quantized SL2 over the complex numbers. So this is how you can use the result of the DeComer and this theorem here, plus the theory described before, to produce examples, to produce, say, for example, Dirichlet forms on these locally compact quantum groups. So in the last few minutes, I want to return to this question of the studying of the domain of the generator. So remember that that's something I mentioned before. We have this result jointly with Martin that when you have a convolution semigroup of states on C0U of G, then it always admits a densely defined generating function. So you can always differentiate at 0, and you can do it for a dense set of operators. We do not know anything about the structure of this set. So here is the trick. There is a definition of something which, again, I don't even want you to look carefully at this definition. Essentially, you define something which you should think about this as these are Fourier transforms of positive measures on the dual group. Whatever that means to you. I mean, there is a certain space which has this beautiful property that if you take a convolution semigroup, I have to put an additional condition. Namely, I have to assume that these states are invariant under this unitary antipode. But remember, this is in the end the class that I'm mostly interested in because this leads to KMS symmetric semigroups on a von Neumann algebra. Okay, but if I have these invariant states, then if I take the domain of gamma, if I intersect it with this strange space, then what I obtain is a dense star subalgebra of C0U of G. So in particular, what it means that domain of gamma always contains a dense star subalgebra. Now, why is this important? Well, for us, I mean, that's a result that we wanted to prove for a while. It's kind of aesthetically pleasing because once again, you have an algebra inside the domain. But moreover, this allows you in principle to study some cohomological questions, right? So because you now have an algebra in the domain, canonical to a certain extent, although why do I say this algebra does depend on gamma? It's not true, or we don't know if it's true, if I bring you two different gammas, whether I can find a subalgebra, dense subalgebra, which will be contained in the domain of both. But at least for a single gamma, I can start looking at some properties of gamma on this subalgebra. So once we know that we always have a subalgebra, you might also ask, okay, what about the characterization of generating functionals? So again, classically, or in the compact setting, we had this even only if result. So if somebody brought you a gamma on a nice domain, you could verify whether this gamma comes from this construction, whether this gamma is a generating function. So here's a result that I want to, again, finish with. This result tells you, again, I don't want you to focus on all the particular conditions, but it tells you that if you have a dense unital RU invariant star subalgebra of the unitization of C0U of G, and if you have a functional on A, which satisfies some natural conditions, if only this A is nice enough, and if only this gamma is nice enough, so for example, it's lower semi-continuous in a certain sense, then this gamma does indeed come from the construction I described. So strictly speaking, I mean, we should say that the extension of gamma generates a convolution semigroup of positive functionals. So this result tells you that, okay, there is a chance to define gamma first on a certain algebra. If this algebra is nice enough, then you can just deduce that this gamma does generate convolution semigroup of states, positive functions. Okay, so let me just finish by telling you, I mean, what we would like to know. So the first question, I mean, it's a kind of question which comes up very often in the context of quantum Dirichlet forms, namely, Fabio Cipriani and Jean-Luc Sauvageau showed already, again, more than 20 years ago, that in the tracial case, quantum Dirichlet forms, these always arise canonically from certain derivations. If you wish, I mean, kind of a very informal way of saying this is that quantum Dirichlet forms are always square roots of Laplacians. Right? Now, in the case of convolution semigroups and compact quantum groups, this actually takes the Cipriani-Sauvageau decomposition takes even a simpler form. And this is related to the Lévy-Khinchine formula or Lévy-Khinchine decomposition for classical Lévy processes. The question is there such a result in the state case? Namely, could you always do a quantum Dirichlet form on a von Neumann algebra with a non-tracial state? Can you always associate with a nice derivation, say a twisted derivation possibly? So there is, we still don't know. And the last result, the last question I want to ask is the following. So in the classical context and also in the compact context, we always saw that these semigroups of measures, semigroups of states, convolution semigroups of states, they have generating functionals which are defined on a canonical subalgebra. So for the classical context, I talked to you about twice differentiable compactly supported functions. In the general compact context, I talked about Pol G. What we have so far for the locally compact quantum groups is just the fact that for every functional, there is an algebra. So the question is there kind of a nice algebra which will always be in the domain of every functional every generating function on locally compact quantum group. So that's the last question I wanted to ask. Here are some preferences for what I talked about, and thank you very much for your attention. That's all I wanted to say.
Thank you very much. Questions, comments? I'm afraid I can't see.
Maybe if I stop sharing my screen, I could. No, if I stop sharing my screen, maybe I can see there. No.
Maybe you can see the questions, right? Good. No, not really. Adam, I do have one question. So
Sure.
my stupidity maybe. So if you've got a semigroup, usually you can, it's a contractive semigroup. It's really, you can always dilate it to a group, right? So what happens in this case? Can you do the same thing here? What happens if you do that?
So you see, so here in kind of the dilation, dilation questions are studied a lot in this context, but usually dilation means something slightly different. So dilation means not the fact that you have a one parameter semigroup that you want to dilate to a group, but rather you have a one parameter, you have this kind of semigroup indexed by positive time, and you have this semigroup indexed, each individual PT is a completely positive map. Yep. And now the natural question is, we know that you can kind of dilate a completely positive map to a star homomorphism. That's essentially a Stein-string theorem. So the question is, when can you dilate to a nice
the whole semigroup, yes,
star exactly, in a kind of compatible way? And that's something that has been studied a lot, and the extra structure which comes from these convolution type semigroups is helpful. So the results, and again, this has probabilistic interpretations that goes back to the work of, I think, Kummer and Masson. Some other people also looked at that. So it's kind of rather, I mean, the dilation it's mostly kind of looked at in this context.
So, but you don't really have a, so the two theories seem to be slightly separate, right?
Yes, yes, exactly. Although, for example, you know, if you can dilate things to a semigroup of automorphisms, then you are in relation to the group, right? Because you just put alpha minus t equal alpha t inverse. So here's where they connect, in a sense.
Yeah, okay. I think I need to think about it.
I have a question, Richard.
Yep, Fabio.
And Fabio. The fact that the question of the existence of derivations on the algebra you constructed in the last slides is connected to the hope to study the K-theory of these locally compact quantum groups through these algebras, the K-theory of these algebras. Is this your hope?
Well, I must say we didn't think about this, but that's definitely kind of a very natural question, right? Because in the idea, you should think that when you have natural semigroups, you have kind of natural, say, I don't know, Laplacians or whatever, you should be constructing natural derivations, and hence they should carry some K-theoretic information, right? The corresponding, I don't know, spectral triples or whatever, they should carry. But I think that nothing really has been done in this direction.
Especially if the derivations are closable on that are unbounded but closable on that algebras, then the K-theory should be the same as the K-theory of the sister algebra. No? Thank you. Jean.
Yes, hi.
Hi.
I have a question on this problem. In many cases, these generators of semigroup are given by something that is called the Limblad formula. And there is a formal generalization of that to the case of general sister algebra, which involve indeed the existence of a derivation into something which is more like Arveson's type of derivation, where instead of having a derivation with value in the same object, you have a value into something where this object acts to give a bimodule. Okay. Now, I've never seen anything about whether or not these derivations have a domain that is well defined and sufficiently good. Okay. So in particular, whether this derivation can generate a kind of the equivalence of a one parameter group. Okay. So my feeling is that there is, in the general case, there is a way of distinguishing among all these generators, the one which are regular enough to ensure that this derivation is regular. Okay. So do you have anything to say about that, or is there research, I mean, things like that's been done?
So maybe the only thing I can say is that you do see at least some elements of what you would ask in this construction of Fabio and Jean-Luc, Cipriani and Sauvageau in the tracial context. So precisely they constructed by module, the construction is canonical in a certain sense.
Yes.
I do not remember whether Fabio might remember whether they study some regularity properties, but essentially I would say that their construction is sufficiently canonical, is that you see that what they produce is the right thing.
No, but it's not my problem. My problem is because the Limblad operator can be, the Limblad form can be developed in a fairly general context and sister algebras, okay? But I have built some examples where this derivation is not good enough in terms of regularity, okay? And I have examples coming from statistical mechanics that obviously are not working very well for the purpose of the general theory, okay? So the question is whether it's possible to characterize the case for which this regularity is guaranteed.
So here I don't know. I don't know.
Yes.
I mean, that sounds like an interesting and important problem.
Yes.
Because that's really like, you have kind of essentially you have a nice domain and you have some object. Well, but when is it kind of regular enough to build a semigroup?
Okay.
Thank you. I will try to look
Thank
at
you.
this.
Thank you. Any more comments, questions?
That's good.
Yes, may I ask what you're feeling? You said something tantalizing at the end about the possible existence of a canonical algebra for a domain, for a core for generators. Have you got some evidence for or against?
Well, you see, I mean, kind of no serious evidence, but I would say that the fact that what we construct, right, this algebra in the domain, it's kind of canonical and not, in a sense that, well, it depends on gamma, but you always intersect the domain of gamma with a fixed thing.
Mm-hmm.
So, of course, the idea is that maybe if you look a bit harder inside this fixed thing, so maybe you don't take, I don't know, Fourier transforms of positive measures, but you take Fourier transforms of very, very nice measures in some sense. Maybe that would give us something, but we definitely do not have any even any computation to justify that. But maybe this is the good direction, right? It's Fourier transfers of something.
And you said it extends to a generator. Presumably, you mean it's a core in a sense. Yeah.
Well, yes. Although, so here again, I was cheating a little bit in the definition I showed you, because I mean the theorem is kind of correct as stated, but for example, for the theorem as stated, we don't even know whether you have whether really restricting of gamma to this particular domain already generates a semigroup. It's not determines the semigroup in a sense that there could be two different gamma. I mean, it's kind of, there's not whether there's a one-to-one correspondence.
Right.
It extends to a general. So maybe let me just use this to ask kind of one question, which I find very interesting. The question is as follows: take two Dirichlet forms and assume that one is contained in another. In general, it's not true that they coincide. That's actually kind of the classical examples which tell you that you cannot hope that this will be true. I mean, so you will get different semigroups. If you have two translation invariant Dirichlet forms, then this result is true classically. Right? If you have two translation invariant Dirichlet forms, one is smaller than the other, they actually are equal. And that's essentially coming from the fact that you have this canonical domain, which determines everything. So we have no such result in the quantum setting. So in principle, I don't know what the answer is. Could you have two translation invariant Dirichlet forms, one strictly contained in another?
Interesting.
Or maybe still to rephrase it once again, forget quantum groups. What else do you need to assume about two Dirichlet forms which will make this result true? That if one is contained in another, they're really the same. So this is really, of course, a question of extending self-adjoint operators and whatnot.
Thank you, Adam.
Welcome.
So, seem to be no more questions. So let's thank the speaker again. Nice lecture. Thank you very much. And see you guys again in a week's time. Thanks. Bye.
Bye.